Hello everyone, this is the uh, week 12 of our live interaction session. Today I'm going to be discussing the segment number 12, which was rolled out the previous year. Feel free to pitch in your doubts as we move along, and I'll try to answer them. So, with that, yeah, so this is the week 12, and we'll be discussing the assignment number 12. So the questions which were given in this particular assignments were from induction motor and also from DC motor. So yeah, the first question was based on speed regulation. So the speed regulation of a motor is given by the no load speed minus the full load speed divided by the full load speed, right? Where n is in RPM. Like you can choose n in whatever whatever scaling you want, like in rotation per second or in RPM, rotation per minute. It does not really makes a difference because the units are just going to match top and the bottom. So also the frequency is related to the rotation as np by 2, right, where n is in RPM, right? Or you can write it as frequency is equals to np divided by 120, where rotation per second, this was in rotation per second, and here the n will be in RPM, which is RPM, rotation per second, and this is rotation per minute, right? So this is the more commonly used unit, that is the rotation in rotation per minute, and is widely given for any machine. So this is why this particular formula is more prevalent, like you multiply the n with p and then divide it by 120, and P here is the number of total number of poles, right? So total number, remember that you are not using pole pair, you are using total number of poles. So this particular formula can help you figure out what is the frequency. Since in our case frequency is given to us, but the n is not given to us, we can find what is the synchronous speed of the motor, right? So if we'll put here values, so the value is 50 is equals to n into 4 divided by 120. You will get n as 1500, right? So this is 1500 RPM. All right, and this is the synchronous speed of the motor, right? But then the motor would be rotating with some amount of slip, as would have been taught to you, right? So for figuring out what is the rotational speed, all you need to do is 1 minus slip into the ns, right? So what is this ns? Ns is nothing but the synchronous speed, and this is what r is the actual speed of the rotor, right? So you have calculated out the value of ns to be 1500. You have your slip given to you as 0.03, right? 3% means 0.03. You can figure out what is the value of nr, right? So NR at no load, because I'm using 3%, which is the no load thing, right? So uh, in this N into NL, which is the no load thing, will be given as 1455, and similarly if you'll put the other thing in the formula, it will become N full load is going to become 1410, right? Now if you will substitute this no load speed and full load speed in this particular equation number 1, you will get the synchronous regulation, like speed regulation as 1455 minus 1410 divided by 1410 into 100%. This gives you a value of B, that is it would be around 3.19, so it is basically falling 3.19, so it is basically falling in category number B for this, right? So that is the correct answer for question number 1. I'm hoping that you understood it. And let's now move to question number 2, right? So in question number 2, what's given to you is a squirrel cage induction motor. So induction motor is basically of two types: a wound cage induction motor, wound rotor induction motor, and then squirrel cage induction motor. The difference between the two of them is that you can change the resistance of the rotor in a wound rotor case, but you cannot do so in a squirrel cage induction motor. I'm sure that the professor would be covering all these things in the regular lecture, but then that's just information. So what's given to you is that the rotational speed of the motor is given to you. Okay, let me switch back to the red ink. Okay, so the rotational speed of the motor is given to you. Therefore, the slip is given to you, and so you can just write it here. The slip is equals to 1500 rpm, because we have calculated out what is the synchronous speed, right, for a 4-pole machine in a previous question. So it is 1500, and minus 1440 divided by 1500, this is going to be, just let me put the value, 0.04, right? So this is the slip, and the shaft power in the mechanical loss. Okay, so the thing is that you have your stator input, power input to stator, right? And then you have your stator losses, stator losses. Then you have your PG, that is your air gap power, and then you have your rotor losses plus mechanical losses, mechanical losses, and then you have your shaft power, right? So shaft power is nothing but the power actually which is being utilized to drive a particular thing, right? So if you fall back, this is the input power which is given from the electric supply unit, right? So electric supply unit, you give some power, you will have some stator losses. The stator losses will be in copper losses plus core losses, right? And after that you will be getting some air gap power. You subtract the ohmic losses here, again the copper losses of the rotor, plus there is very less amount of core loss in the copper as well, very small amount, right? So this is the rotor loss, copper loss plus core loss in the rotor. And after that you will have some mechanical losses. Mechanical losses are friction and windage loss, and other losses associated with the slips. And then finally you will end up with the shaft power, which you are using for driving the application. So this is how the power flow diagram is for a regular induction machine. Now in the question it's given to you that the shaft power is given to you. Now this shaft power is equals to 2700. It's given to you in the question, right? And mechanical losses are also given to you, right? So shaft power, P shaft is equals to 2700 watts, and P mechanical is equals to 180 watts. This is also given to you in the question. And stator loss is equals to 0.6 times the rotor loss. So what is the rotor loss? P rotor loss, right? So this is nothing but 3 times I square into R2. R2 is what? R2 is the resistance of the rotor, right? So if this is the rotor, then P of stator loss is equals to 0.6 times of 3 into I square into R2 as per the question, right? 0.6 times. So this is everything which is given to you, right? Uh, so if you will see, these three are forming the total loss in the system. This is the total loss of the system, right? And this is the useful output power, P out, right? For figuring out the efficiency, you can use that P efficiency is equals to P output divided by P output plus P losses, correct? So this is all you need, right? The P output is already given to you. All you need to figure out is that what is the value of this particular unknown quantity, right? How to figure that out? Uh, you can figure that out from this particular these two particular information which has been given to you. So the PG is also known to you as I square into R2 divided by S into 3, right? So this particular formula has been taught to you in your classrooms, right? And we know from this particular energy diagram that PG is nothing but shaft power, which is 2700 in our case, plus mechanical losses, which is 180 in our case, plus 3I square into R2, which is the rotor copper loss, right? Now if you'll see this particular equation, let me call it equation number 1, you can see that there is only one unknown in this equation, that is I square R2. The other thing, which is S, we already have an information of it as it being equal to 0.04. Now if you put S value of S and then try to solve this particular thing, you will end up getting that 3I square R2 is equal to so I have calculated it out, it would be 120, right? And then if you are going to put this in the losses, right? uh, you can figure out the value of the total amount of loss, right? And then the output power is already known to you, and then you can use the equation number 2 to figure out the efficiency. So if you'll see, the equation number 2 will be equal to 2700 divided by 2700 plus, it would be 300, let me see what I've written, it would be 370 something, 72, yeah, 372, right? So you can solve this by substituting in the value of power loss, which is equals to 372, and once you substitute in the values, you will get the efficiency as, let me write it with separate ink. You will get the efficiency value as efficiency is equals to 87.8%, right? Which is kind of falling in this particular range, so A becomes your correct answer. So this is how you are going to solve this question. If there is any doubt, you can see the recording, right? And then you will be able to again kind of go through the recording again, and then I think it will clear your doubts. So let me move on to question number 3 now. So for question number 3, yeah. So question number 3 is delta connected induction motor with four poles. It has the shaft power of 25 HP, right? Let's switch back to red. So it has a shaft power of 25 HP. 1 HP is equals to 746 watt, right? So you can have your power in watts. Okay, so the shaft power is given to you, and the rotation speed is given to you. Therefore you can figure out what is the slip of the system, right? For our case, let me just figure out what is the slip. So it is 1500, because it's a 4-pole machine, right? And 50 hertz, so we have calculated the slip synchronous speed as 1500 in the first question. So the synchronous speed will remain the same, and the rotational speed is given to you as 1475. Therefore, uh, the slip will become equal to this particular quantity, which is equal to 1500 minus 1475 divided by 1500 is equals to uh, 0.10166, right? So this is the slip of the system, right? And the shaft power P shaft is given to us as 25 HP, or equal to 25 into 746. So 18650 watt. This information is also given to us in our question. And the power factor is given to you, right? So that is all right. We will take this information. The mechanical losses and the iron losses are zero point 0.4 HP and 0.6 HP. So the total mechanical plus iron loss is given to you as 1 HP. Mechanical plus iron loss. Mechanical plus iron loss, Fe loss, is given to you as 1 HP or 746. This is also given to you, right? Now, the stator circuit loss is given to you as 1800. So stator loss is given to you as 1800 watt. So I've just written down what is given to you in the question, right? I have not done any calculation now. I have just written down what is given to you in the question. Now let me just, for the purpose of clarity, again revisit the power diagram which I had shown you in the previous question. So you have your power supply coming in from the grid or the input, right? This is the electrical power which is being fed to the induction motor. Now the induction motor is going to have some amount of stator loss. So this is your stator loss. Let me use blue color. So this is your stator loss, right? This is your stator loss. Now stator loss can be divided into two parts. That is the copper loss, which is occurring in the stator, plus the core loss, which is occurring in the stator, right? You subtract the stator loss from the input power, you will get the air gap power, that is labeled here as PG, right? Now this air gap power gets transmitted to the rotor, right? And the rotor will have its own losses. Now let me just show that with green color. So the rotor will have its own losses, which will be the sum total of the rotor copper loss plus the rotor core loss. Normally the core loss of a rotor is very low. It is only the copper loss which is there in the rotor, right? Now after subtracting this rotor losses from the air gap power, you will end up with the total power, which will be shaft power plus mechanical losses plus the iron and the windage losses, right? So this from power from this end, if you subtract the mechanical power losses, there would be some losses in the bearing of the machine and so on. So if you subtract the bearing losses, mechanical loss, you will end up with the shaft power, right? So let me just use different ink for this. Okay. So shaft power is nothing but the actual power which you are getting out of the induction machine, which can be used for driving any application, right? So this is the useful power which you are getting out of the system. So you gave in the electrical power, here, and you got some useful power here. Everything in between is non-useful power, which is kind of losses. So with this particular information, let us again revisit question number 3. So yeah. So what's given to you is the shaft power, right? shaft power is given to you, and then the mechanical power loss is given to you. This is the total mechanical power loss, right, which is the sum total of mechanical loss plus iron losses. Iron loss is nothing but the core loss, which I told you to be very small quantity, right? So in this particular case, it's some meaningful quantity as given here. It's 0.6 HP. So if you will add up the shaft power plus the mechanical power loss plus the core loss in the rotor, iron loss in the rotor. Core loss and iron loss is the same thing, right? Uh, core loss in the rotor as Fe loss I have written. Okay, so let me retain the nomenclature. And then if you are going to add up the rotor loss in the rotor copper loss in the of the machine, you will end up with a air gap power, right? So this is from the power diagram I had shown in the previous page. Also I had written that air gap power is nothing but I square R2 over S multiplied by 3, because this is a 3-phase machine. So you will end up with air gap power as is mentioned here, right? Now from equation number 1, I can write that air gap power is nothing but the shaft power, which is 18650, right, plus the mechanical plus iron loss, which is given to you as 746, plus the rotor copper loss, which is nothing but I square R, right, 2 R2, because I'm on the rotor side. So the value of S is given to you as 0.016, right? So you can substitute in the value of S to figure out what is the 3 into I square R value from this particular equation. Let me call this equation number 2, right? So from this equation you can figure out what is the 3 into I square R2, and you will figure it out as 328.74 watts. All right. So now if you will use the value of S again to divide this quantity 3 I square R2, then you will have the value of PG, right? And the PG value will be equal to 19724.7 watts. I've done nothing. I've just divided this I square R2 divided by S, which we have formulated previously. So if you have your PG with you, all you need to do is add the stator losses. So I have the power input is equals to stator loss plus PG, right? This is the power input as per the energy diagram which you have shown previously. So stator loss is given to you as 1800 watts, and we have figured out the value of PG as 19724.7, right? You can add both of these two together to get the value of power input. But we also understand that let me use different ink now. We also understand that power input is equals to root 3 times of V line to line into I line into cos theta. So root 3 Vi cos theta, right, for an induction machine. We understand that this is the formula, and here we have figured out the total power input, right? So the total power input is nothing but 21524.7. You add both these things together, you will end up with this particular quantity, right? So if I'll equate this to 21524.7, I should get the value of IL, right? Because everything else is known. V line to line is known to you as 415. The cos theta is also given to you as 0.85 lagging, and rest all the quantities are known. So the value of IL will come out to be 35.22 ampere. So which makes the option number D to be the correct option, and thus that is the answer. So I'm hoping this answer was clear to you. If not, feel free to pose in your doubt. I'll try to address them. Okay, so if there are no doubts, I'm taking that you understood the problem. Let me move on to the next question now. So the next question is related to an induction motor again, right? So yeah, so it's a Y-connected induction motor, right? The windings are Y-connected, all right. And the total output power is given to you. That is the shaft power is given to you as uh, 15 kilowatt, right? So the torque is required at full load condition, right? So if you want to figure out the torque at full load, you must have the rotational speed in radian per second, right? Because torque is given by the formula that torque is equals to power out divided by omega r, right? So omega is in radians per second because you are using standard systems, SI systems, right? So it must be in radians per second, and the power also must be in watts, right? So power is given to you as 15,000 watts, so no question, no problem there. Power out is given to you as 15,000 watts, right? And the ns value is also known to you because this is a 4-pole machine, 50 hertz. So just like in the first question, ns will ns will be equal to 1500 rpm, right? And if you want to figure out what is nr, you can just multiply it with n 1 minus s into ns is nr, which will give you the value of nr, right? But if you want to figure out what is the omega r, then you need to 2 into pi into frequency. And what is the frequency here? The frequency will be mechanical frequency, of course, here. So it will be equal to 1 minus ns divided by 60, because we are converting it from per minute to per second frame, right? So this is there, and then if you substitute in the values, you will get the value of omega r as 48 into pi, right? So if you have this particular value of omega r, if you have the value of p out, then you can figure out what is the torque by substituting in this value. So 15,000 divided by 48 pi, this gives you 99.47 Newton meter as your answer. So C becomes your correct answer. So I'm hoping this particular problem was clear to you. If not, please feel free to pitch in your doubts. I'll try to address them. All right. Uh, so I'm taking that if there is no doubt you have understood it, and I'm moving to the next question now. So this is question number 5, which was there in assignment number 12. Uh, a DC series motor is drawing. So this is now a DC series motor question. Is drawing an armature current of IA, is operating under unsaturated magnetic condition. So what do you mean by unsaturated? So we know that flux is proportional to IA, that is the armature current, for a series motor if it is operating under unsaturated condition, right? If it is not operating under unsaturated condition, pi will not be proportional to IA, right? For a DC series motor. So this question is basically stating that phi is proportional to I. This is there in the question. Now you are required to find the torque developed in the motor as a function of IA, because all the options are in IA, right? So I know that the torque is proportional to K phi I, or you can write torque is equals to K phi I. torque is equals to K times phi into IA, right, for a DC series motor. So I'm sure that the professor would have covered this the derivation of this formula in the classroom. So you can refer to his notes how this formula is coming. But then this is the formula for torque in a DC machine, right? And phi we know it to be proportional to Ia, right? Again the armature current. So you can write torque is equals to Ki square, right? And if you remove this proportionality constant, you can just write torque is proportional to Ia square, right? So if this is the situation, then C becomes your correct answer, right? So I'm hoping that you understood this particular problem. The thing to carry back from here is that you just need to pay attention to this particular term over here, that is unsaturated and saturated magnetic conditions. Uh, so if there is any doubt in this question, please feel free to ask. Okay, so I take you have understood it. So let me move on to the sixth question now. Uh, this is a 6-pole DC generator which is running at 1000 RPM, right? The frequency of the current in the armature winding is given by what? So the formula for frequency remains the same, right, as was in the induction motor case. So it will be nothing but uh, what is frequency? It is the total number of electrical rotations per second, right? If you're talking of electrical frequency. So electrical frequency is nothing but mechanical frequency into the number of poles by 2, right? And what is mechanical frequency? Mechanical frequency is nothing but the rotation per minute divided by 60, right? This is the mechanical frequency into the poles divided by 2, just from here. So this is what I had done in the first question. This is how you derive the electrical frequency, and therefore you have NP divided by 120, which is coming to you. So the formula remains essentially the same as the induction motor. No changes there. And the n value is given to you as 1000 rpm, the p value is given to you as 6, 120 is here, so you will end up with 50, right? So this is there for, so the DC generator would be generating electrical power. The frequency in the armature winding will be equal to 50 hertz, right? So I'm hoping that you have understood this particular solution as well. If there is any doubt, please feel free to ask. I'll try to address it. Okay, so if there is no doubt, I'm guessing that you have understood it. So this winds up this particular lecture series. So today was the last live interaction session, right? If you have any queries in the previous assignment, I'll recommend you to revisit the interaction sessions which has been posted on the YouTube channel, and revisit the solutions there. I'm sure that you will be able to understand the problem. So as a part of this particular coursework, we have covered a few things. The first one was circuit theory, right? So there we studied many things like KCL, KVL, uh, right? Those things, and then the circuits and the problems based on that. Then we moved on to little transformers. So transformer, few questions we solved, right, over the course of our interaction sessions. And then finally, as a conclusion, we are heading towards induction motor and DC motors and generators, right? So this was all which was covered in this particular interaction session. I'll recommend you to read also from some books which would be there like advised by the professor. One very common book which students utilize and is reasonably good for any competitive examination is the book on electrical machines by P.S. Bimra. It has a reasonable number of solved questions as well as a good amount of theory. If you'll read through it, you will understand a reasonable amount of electric machines. And it will be helpful in your competitive examinations, which you will be writing in days to come. So that was all from my side. I'm hoping that you enjoyed this particular interactive session series. Uh, thank you, and then feel free to join in the next interactive session by my colleague. She would be taking it for that she would be taking in for the next 1 hour. So thank you again. I'll be posting this shortly on my YouTube channel, and then you can see the videos there.